So welcome everyone to Üçgen seminar series. So today our speaker is Ayşegül Öztürkalan from Abdullah Gül University. She will tell us about loops in moduli spaces of real plane projective curves. Please.
Yeah. Thank you. Thank you for inviting me here. And it's great pleasure to be here, to be in this community. I'm from Abdullah Gül University, but originally I'm graduated from Bilkent University from PhD, and I studied with Alexander Dektyarev on sextics, especially simple singular sextics was the main point for me. And later I have been in Stony Brook University and I had the chance to study with Oleg Vero, and we studied on non-singular sextics. I will tell the details. You may say non-singular sextics are classified, everything is known. However, the moduli space topology of moduli space is not investigated up to now. So this is a new attempt, okay? At first, let me introduce you here, the overview. At first, I will tell about curves from the algebraic perspective, algebraic geometry perspective, and then I will tell them in terms of topological perspective and isotope classification of curves, which have done for most of the degree 6 curves. I mean, just irreducible parts is open still. Irreducible and singular parts is open, but non-singular and simple singular parts are closed. They are defined. I will tell about these things. And main question, what is the main focus of my study? I will tell about it, and the construction of the proof and the results I will give. At first, let me start with defining curves from algebraic perspective. I suppose you are familiar with these things, but once more, let me remind these things. Let us say CD as a plain algebraic curve with degree D in real projective space. So what does it mean? Here is by CD, I'm telling about, okay, can I write this one? Let me check. I'm telling about fx, y, z. Of course, it is in projective space, so it will be homogeneous coordinates. And this will be ai, j, k, here x to power I, y to power j, and z to power k. And of course, these I plus j plus k will give us d. And these type of, for fixed degree d, the space of all these curves with the same degree, let us call them as RCD. Since it has homogeneous coordinates in projective space, here with the number of coefficients is d times d plus d over 2, which will give us dimension of that space. And let us call R and CD, which contain which will be the space of non-singular curves in that space. It will just spare non-singular ones. And notice here, any non-singular curve, okay, here let me say any point here will be a curve. So for any curve, if we are talking, any non-singular curve has a neighborhood in RCD consisting non-singular curves, and boundaries are singular curves. What does it mean? It means this is a subspace in RCD and it is open in RCD. And the boundaries are singular curves. Boundaries are singular curves. What I mean, for example, when you have a curve consisting two ovals, here if they approach here, they are, when they approach more, we obtain a new curve which have singular point. Okay, so this is in the closure of these points. Okay, this is from algebraic perspective, but whenever we look from the topological perspective, these curves, we say isotopy, notion of isotopy. Indeed, let me remind you what is isotopy. Isotopy is here, this is the formal definition. Two real curves with the same degree are isotopic if there exists a fiber-wise continuous embedding of C into the projective plane, such that the starting point is C and ending point is C tilde. Here it means we have two different embeddings, and we need to deform these and one of these embeddings to another one. For example, here, if you have such a curve, you form it, you deform it, and it can be deformed to oval. Okay. However, when you have a node, it's not isotopic to when you have a node. I'm not good at drawing this node. Okay, it's not isotopic to an oval. Okay, and with these isotopy notion, some classifications are done for degree for curves up to degree 6. They are done, but at first let us try to understand what is a non-singular curve. Indeed, whenever you imagine non-singular curve, but real, this is important, non-singular real curve, it consists two types of elements. It is combinations of one-sided components and ovals. Indeed, whenever you think about, for example, a degree 3 curve, if it is degree 3, you have a component like that and an oval. Or it becomes just, it becomes just a one-sided component. This is one-sided component and this is oval. So if you have a degree 3 curve, it is either like that or like that. Indeed, one-sided component is the component, this is one-sided component, this is oval part, okay? We have one-sided components in odd degree curves. For example, these are the schemes for degree 4 curves. Whenever you want to have, for example, if you have something like that, this may be a degree 4 curve, because whenever you draw a line, it intersects at most 4 points. So this can be prescribed by degree 4 curve. However, when you say two oval and a line, it must be at least degree 5. This can be at least degree 5. Because here, you know, this is 3, but this cannot be 3. For only 3, you have 5 intersections, and it can be described at least with degree 5. And because of this one-sided component, it must be odd degree. It may be 7 or 9 degree, but at least it is 5. These classifications, indeed, these classifications are done up to 6, as I said. Okay, here I put degree 4 schemes. Indeed, these classes, these classifications, each class are called schemes. Why schemes? For example, when you have something like that, it is the same with this one. It means two components which are homotopic to oval, but one contain another inside of it. Okay, so a degree 4 curve can be either like that, or like that, or like that, or like that, or this, or no oval. If it has no real point, then it has no oval. Okay, so these are known, and moreover, degree 6 non-singular real curves are also known. And these classifications are done by so many people contributed to this classification. However, Gutkov completed this classification. And this picture gives us this classification. What does it mean? Here, let me try to tell you. This, for example, when I say 3 union 1, 2, it means 3 ovals we have on the outside, 1 oval here, and 2 ovals inside. There exists a scheme containing these ovals. Indeed, it must be like that, because here, if you divide it by bezo, you know, 1, 2, 3, 4, 5, 6, it intersects at 6 points. And when you take this, it divides with 6. When you take this, it divides 6. When you take this, it divides 6. For example, this class cannot be like that. I'm sure that it cannot be like that. It is not like that scheme. Why? Because when you intersect, it will need more degree than 6. Okay. Is there any I don't know if I'm going so quick, so fast, but if you have any question, you can stop me. And with these classifications, there is one more thing that we need to regard. It is type 1 and type 2 forms. What are these? Type 1 forms are the curves dividing complex curve into 2 halves. What does it mean? Indeed, we are dealing with real parts of these curves. However, a non-singular curve has also complex part. We just deal with real part of it, but type 1 curves are these. Whenever we take out real part, here, for example, it has complex. Whenever we take out real part, it becomes 2 halves. It becomes not connected. However, type 2 curves are not dividing. What does it mean? Whenever we take this real part, still it is connected on the other side. Okay, here type 1 and type 2 curves, according to type 1 and type 2, this list is given here. And here blue ones are type 1 curves. And here red ones are type 2 forms. And the purple one, this is purple, for example, this is type 1, contains type 1 and type 2. Both of them it contains. So here, for all these schemes, we have here more detailed ones. For example, when you have 3 ovals nested inside, this exists only with type 2 curves, with real degree 6 curves. The good side of this classification is this. It says that every type 1 and type 2 curves with specific schemes are unique. What does it mean? If you take this class, this is 8 ovals, 8 empty ovals. Indeed, any 8 empty oval is isotopic to each other, and it is contained in one space. This space, the space of 7 ovals, is connected, pet connected. Every part is connected. Okay, and these are known, studied, and well-known parts. So what is the point? If all these things are known, what is the point? Indeed, the question that we studied together with Oleg Vero is this question: what is the fundamental group of each strata? Here, by strata, we call these classes. Each classes, for example, when you take this one, or I said this, you know, this is type 1, 7 ovals class. What is the topology of this class? Okay, I said it is unique and connected, but if it contains any loops inside of it. And this is very general question. And I specifically focused on the fundamental group of 9 empty ovals with type 1. Here, space of, this is SI9, means space of degree 6 curves of type 1 with 9 empty ovals. So I choose this part to study. It's type 1 version I choose. Why I choose this? Because here, whenever you have, for example, this is the this looks most complicated ones, these looks. However, here it is contained inside of each other. The rest lies inside. So it is hard to move here. Whenever you draw a line, it intersects already at 3 points. So I cannot pull any point from here to here because it will contradict with Bezo theorem. So any oval here cannot move here to here. So these are, if they contain nested ovals, it will be a more restricted movements. There must be more restricted movements. So it's not very interesting to study the fundamental group of this space. Indeed, the smallest obstruction may be here or here, and I choose this one because of the constructions that I will tell you. I choose 9 oval ones because 9 oval, here when you have 9 oval, there are so many freedom. They are so free because here, you know, we have 4 on this, so I can move this oval to here. It can pass through this one, but of course, it must not be intersected with the others. I'm not sure if I'm able to tell it here. If they can intersect at more than 6 points, it will be an obstruction. So I need to be carefully investigate. I need to investigate carefully where to move each oval. Okay, to understand the movements of ovals, here I'm looking for the fundamental group, so I'm looking for the movements of ovals to each other. So I have 2 different constructions to understand this. The first construction to obtain 9 oval is that way. Here we consider non-singular cubic F. Here, one component here and another oval here. This is a cubic. And a sextic G, degree 6 curve here we have. This is G. And it is cutting F at 18 points transversely. Here, without tangency, it transversely cuts F. And here, whenever we say F squared plus TG equals 0, this is a perturbation. And by this perturbation for non-zero T, we obtain 9 ovals. How it happens? Indeed, here, this is F squared plus TG. So with F squared, we have double here. Okay, these are all doubles. And whenever we have TG, with this, with positive T, it will be like that and like that. We will have, and here another oval, and here this is empty, here this is, it will be like that for one sign of T. If you change the sign of T, I mean, if it has positive, with positive T, if you have this picture, these ovals, let me take it back, with negative T's, you will get these parts. Again, it will be 9 oval. Here you have something like that. And again, it will be 9 oval. So by this perturbation, we get 9 oval. another construction we have, and this construction is taking intersection of two cubic curves. Here we consider a non-singular cubic F with this blue one, and another cubic G, which is the red one, and it intersects F at 9 points. You know, two cubics can be intersected at most 9 points, and here we get the most points. Here we have nine intersection points. When you have this, when you take F squared plus G squared, indeed, when you say F squared plus G squared equals 0, it is exactly just these points on these curves. These are just these points. I'm not sure if this is 9, okay. But when you say minus TH, where H is a positive form of degree 6, and for positive T, we will get something like that. Here, these will degenerate to, perturb to ovals, not degenerate, of course, these perturb to ovals. Okay, so by this way, we will obtain 9 ovals. Indeed, these two constructions are two different ways to get ovals, 9 ovals. However, I will choose this one to continue. Why? Because when we have this construction, it is something like that. Here, if we have F squared plus G squared equals 0, it means in complex side, this is F plus IG and F minus IG. Indeed, this is F plus IG times F minus IG. So we have two sides, and these are the intersections here. And by this way, we get type 1 curve. This corresponds to type 1 curve. By this way, we obtain ovals, 9 ovals representing degree 6 curve. And this degree 6 curve is a type 1 curve. So this is the thing that we want to go on. So we will go on with this construction. Okay. And indeed, while movements of points we are considering, it is the same with, we want to consider if this is the space of ovals, how we turn around these things. Indeed, it is the same with working here, looking at loops on these points. And indeed, so our problem turns out we will use these things, space of divisors obtained by these intersection of two cubic curves. And this space of divisors will lie in the boundary of S9 empty oval type 1 curves. And it has perturbation to 9 oval curves. And indeed, these 9 oval curves, can be taught by 9 configuration points. Configuration points, you know, these are the points that they can go to each other. This may go to here, this may go to here. So which one goes to other one, which one goes to other one? Here, this is configuration points. So it is, this space can be embedded to configuration space of 9 points. So we will look our method in this space, how these points are moving in that space. What do I mean? Okay, I have more examples here. What do I mean? We will look about these things. Here, I have this point, I have this point, I have these points. But can I move this point to here by keeping F squared plus G squared equal to 0? In that space, can I move this point? Okay, I can move this function a little bit here, move a little bit more, but can I guarantee that still it's a cubic? So I can change, okay, whenever this is changed, it will change a little bit more here. But can I guarantee that I will keep these points also? Because whenever I have a tangency, for example, this comes, and here, if I have a tangency, it means instead of 2 points here, I have 1 point. And so it is, from now on, it is not 9 points, it becomes 8 points. So I cannot jump to another space. I want to study in 9 oval space. So I don't want any tangency. I don't want any other function. I want to keep this f and g as cubic functions. And I want to keep 9 points as intersection. So keeping these 9 points and 2 cubic functions, how can I move these points? How these points move around? The question is this. You need to understand that. Let me show you some other easier examples. For example, here when I construct such a thing, here C represents this oval, this small degree 2 oval. This is degree 2. Okay, this is degree 2. And this is a line, this is another line. And here, when you look at this equation, it is here, this is degree 4, degree 4, degree 4 multiplied by degree 2. This is a sextic. This is a sextic. And when you look at this, it is indeed just this oval and 3 points. Now, can I move this oval around these points? Yes, why not? Because this degree 2 curve here, this is independent from others. So by changing equation of degree 2, I can move this to here, move it to around. I can move this curve to anywhere, wherever I want. I can move it to infinity. So it is easy to see that. But this is a movement. This is a movement in 4 point space, 4 oval space. For oval degree 6 curves, we can say this movement. Okay, another example. This is an example. As another example, consider this curve. Here, this C3 is degree 3. Degree is 3. And here, this is degree 2. Degree 2. Okay. Now, this degree 3 is C3. This and this part, 2 component, degree 3. And C2 is just one oval, which is degree 2, and the line I have, okay? And as you can see, it has 7 points. So this is a movement in 7 empty oval space. How they move? For example, if I want to change the line, how can I change? When I change this line, at some point, sorry, it becomes hard to draw a line, probably. At some point, it has tangency. Can you see? So it's not very nice to move this line. Since this is degree 3, at some point it will have tangency, and I cannot move this line keeping 3 points intersection. Keeping 3 point intersection, I cannot move this line. Okay, another way to think, can I move this oval? Yes, I can move this oval. How can I move? I can change this oval like that, like that. So by this way, at the beginning, P1, P2, P3, P4, let me say, if we have, and here P5, P6, P7, if we have. If I put in configuration space these points, I will see that while P1 is going to P2, P2 is going to P3, P3 going to P4, and P4 goes back to P1. What about the rest? The rest stays as it is. They don't move. So we have a fixed line, just we are changing the degree 2 curve. So we have such a movement in 7 oval space with sextics. Okay. However, our work is quite harder. Why? Because we have 2 degree 3 curve, and we want to move this curve in somehow, and still I want to keep 9 intersection points. Okay, to understand this, we divide the space of this space into subspaces. Indeed, it contains A09, A27, A45, A63, and A81. What are these? Indeed, if this is the variety, if we call X as the variety obtained by F, this is, let me say, X0, and this is X1. Here, this is the cubic form obtained by F. And here, if you say Y as the variety obtained by G form, it means here the space of divisors having I points on X0 and the J points on X1. Intersection with 2 curves can intersect either having an intersection as 2 on X0 or 4 or 6 or 8. So on this component, either we have no intersection or 2 intersection or 4, 6 or 8 intersections. Here, this is the example for 2, 7. And this is the example for A63, 6 intersection here, 3 intersection here. And notice that these are disjoint spaces. What I mean, I cannot move the space to that space. Why? I cannot move this curve to this curve. Okay, let us suppose that X is fixed. Take X as fixed. Move Y. Okay, if we move Y, whatever we do, we cannot have more intersection points, because whenever you want to intersect more, if you take this part and some part, you will come to you need to have a tangency. At first you need to have a tangency and then 2 points. If you have a tangency, then you pass to 8 points space. So you lose 9 points space. So to pass from here to here, you need to pass from another space. So it is these are disjoint spaces. And I'm looking if there is something more to tell here. These are disjoint spaces. And now we need to look what are the movements here. If we obtain the movements here, let me say sigma 1, movements here as sigma 2, sigma 3, sigma 4, sigma 5, it may be more movements. I mean, it may contain more movements, but let me represent them just 1. Indeed, the space of 9 ovals, will contain these movements. Why? Because we know that 9 oval space is connected. It is path connected. So in the 9th space oval, these are all connected. However, if we think them as with that space, with that specified space, they are disjoint, and movements in each of these are separated. Okay, how I try to understand the movements here? Indeed, in the proofs of these movements, I don't want to tell the details. I used group law of elliptic curves. And by group law, we obtain some movements. What are these movements? Let me tell about the results. Indeed, in the space of Aij, one shift of points on x0 corresponds to one shift of points on x1. What I mean, on this one, for example, here, if you have, let me say 6, 1, 2, 3, yeah, 6, and here 3 points. Here, for every movement here, if this shifts to this one, this shifts to this one, this shifts and comes from infinity to here, okay? And in a coherent orientation, if you get this movement by changing y, you obtain one shift for each. As I said, with the coherent orientation, if they move in that direction, this move in that direction. So every shift on this one corresponds to one shift on the other component. On the other hand, another one, fundamental group of A09 is identity. What does it mean? If you have 9 points only on this, 3, 4, 5, 6, 7, 8, 9, 10. If you have such a thing, you cannot move these points with one shift. This cannot go, I mean, going infinity, coming here, this cannot go. You don't have such a movement. Here, by changing y, we cannot have this movement. So, fundamental group of this space is just identity, nothing else, no other movements we have. Okay, let me tell this with an example. Okay, the example is another theorem we can say. When we are looking in, for example, A27, here this is A27. So we have 2 points here and 7 points here. So it means we have a curve passing through. I don't know, okay, it's very ugly. Suppose that this is a cubic curve. And when I move this, move here, it will be something like that, taking P1 to P2 and P2 back to P2 to P1. And the rest is shifting to each other. Just here, P9 goes to P3 by visiting infinity. And in configuration space, we show it like that. Here, P1 goes to P2, and the rest are shifting. Just P9 goes to infinity and comes to P3. But here, we also something, also problematic thing. Here also these points has orientation in itself. Why they have orientations? Indeed, if you notice here, these are when we perturb them, they convert to ovals, and each oval has an orientation. So indeed, these points, when we shrink them, they keep the orientation in itself. So if it has this orientation, this point also has this orientation here. So we consider, while sending infinity and taking this braid group, we consider these orientations. So if this has such an orientation, this has an inverse orientation, and they change these orientations. And when we have clockwise, anti-clockwise, and something like that, here, if you have, it carries this orientation to the next one. However, when you have at the last point, if you have, for example, with positive clockwise orientation, when it goes to infinity, the orientation changes and it becomes anti-clockwise orientation because it is projective space. When it goes to infinity, orientation is changing. So we obtain by this way, this is the element of full braid group representing the behavior, representing the movement in A27. And by this way, we represent each of these with sigma, with gamma 1, gamma 2, gamma 3, gamma 4, and gamma 5. And here, this is identity, nothing here. So just 4 elements we obtain to define fundamental group of 9 ovals. This is the end of my talk. But if you want something more, I can tell you more detailed things.
Thank you very much, Ayşegül.
Okay, without stopping, I continued. I don't know if you had any question and something.
Maybe we can ask them.
Okay.
There are now. So any questions, remarks, comments? So yeah, like you gave 2 examples a couple slides before.
Yeah, here.
Yes, that one. So just to be sure that you see there is this C2, right? And then you were talking about deforming it. So
Yeah.
could there be some possibility there also that it causes some tangency with the oval of the cubic in the second example?
In the second one. In the second one here, yeah. In the second one, for example, when you consider to move, for example, if you want to move these points here, this is P1, P2, P3, let me say.
Yes.
If I want to...
Yes, but I was more curious about movement of C2.
Yeah, movements of C2. Yeah, when you move C2, indeed, this C2 is independent from this line.
Yes.
They are not moving together. They have no connection. They are not moving together. So I can change C2, keeping 4 intersection points.
Oh, okay. This is possible. That's what you mean.
Yeah.
Yes.
But we cannot do the same thing with line. Why? Because when I move the line, at some part, okay, I can say here it may be like that. It intersects the 3rd point at some point here. I can take this one more like that, for example, but more like that will give me a tangency here. At some point, I will have a tangency and I will lose 1 point, which means I will pass to another space.
Yeah, I see.
So this will not help me.
Okay. But just moving C2, this would never happen in this up there, like with the oval of the cubic, C2 cannot have tangency.
It may have tangency, yes, but if we don't want, we can move without tangency.
Okay.
I mean, if we want, we can find tangencies still, yeah. But we are looking if we are able to move it without tangency, without losing 4 points. I mean, keeping 4 points. Yeah. If we can do it, then it's okay.
Yes. Okay, thank you. Any other question? So Özgür has a bad connection, you know, he already told, and actually he's asking about the braid group action. So could you tell a bit more about that?
With braid group, okay. Indeed, we consider full braid. This is an element of braid group, for example. This is an element in B7. Indeed, the elements at the end we obtained will be all elements of full braid group. So we are working in braid, we are working in configuration space. So I'm trying to express fundamental group in terms of braid groups. So what I need to tell more, but this is a spatial braid group, not usual braid group, because as I said, they have orientation. Each point has an orientation. I mean, as usual braid groups does not have something like that. Sorry, configuration space does not have. So it's not exactly full braid, but these are elements. I mean, it's a subgroup of full braid group. It will be. Does it make sense?
I hope so. Yes, also Özgür confirms. Okay, if there is no question, then we can thank again to Ayşegül, for which I'll be symbolically also, I guess, for all the other participants. And then I'm stopping recording.